Hello, ladies and gentlemen. Welcome to Module 6, the Data Link Layer. My name is Mr. Tandy at Tandy IT. So before we get going on this video, I have a question for you. Send me an email. What would be a Layer 2 address on your personal laptop or your computer? What would be a Layer 2 address? Send me an email on what that would look like. So let's get into this. The module, we're going to explain how media access control in the data link layer supports communication across the network. Purpose of the data link layer, we're going to describe the purpose of the function of the data link layer in preparing communication and transmission on specific media. Remember that media, we talked about that. The media being like those roads that travel, the way that media, the way the data goes through, how it needs to get there, things of that nature. Topologies. Compare, contrast media access control methods and wide area networks and local area network topologies. And the data link frame describe the characteristics and functions of the data link frame. So let's talk about the purpose of the data link layer. So the data link layer is responsible for communication between end devices and network interface cards. End devices and network interface cards. So the end devices, like a computer or laptop, and the network interface card essentially would be those, those dedicated peripheral devices that are attached to those machines. It allows for upper layer protocols to access the physical layer media and encapsulates layer 3 packets, which is IP version 4, into layer 2. So if you take a look at our picture here, we have our destination NIC, source IP, destination IP. Now, I keep bringing up this picture, and I'm going to keep bringing it up. I can't help but to equate what we do in the real world as far as how this works with this information. Destination NIC, source NIC, right? Destination, source IP, maybe our numbers, source IP, destination IP, 123 Main Street, Anchorage. Okay, that's kind of a good comparison. It also performs error detection and rejects corrupt frames. Now, the IEEE 802 local area networks and metropolitan area network standards are specific to the type of network, Ethernet. The data link layer consists of two sublayers, the logical link layer and the media access control, or MAC. The logical link sublayers communicates between the network layer software and upper layers and the device hardware at the lower layers. The MAC sublayers are responsible for the encapsulation and media access control. So, as you can see here, this is essentially how that works in here. These are all the MAC sublayers, 802.3, 802.11, Bluetooth, 802.15. Here's the physical layer, and as it goes up, into the network layer. So all of this is layer 3, and here is all layer 2, and obviously layer 1 is the physical connection here. Packets exchange between nodes may experience numerous data link layers and media transitions. At each hop along the path, a router performs 4 basic layer 2 functions: accepts a frame from the network medium, de-encapsulates the frame to expose the encapsulated packet, re-encapsulates the packet into a new frame, forwards the frame onto the medium to the next network segment. So let's see what that looks like in Illustrator. I'm going to try to illustrate that here for you. Let me go full screen here, pull out my wonderful pen here. Okay, so it accepts a network frame. So what I'm going to do is I'm going to draw these little circles right here. We're going to call these little routers. And let's just say, for example, we are here in Riverside. I know that's a bad way to spell it because I'm trying to do this on a computer. And over here, let's call this city, I don't know, let's call this LA. Okay. Now, accepts the frame from the network. So let's say somebody in Riverside decides they want to send somebody some information here in LA. that packet's going to go out of that physical medium, okay? It's going to be encapsulated as it goes through that physical medium, whether it be fiber or however it's going to get there. As soon as it shows up at this network, okay, it gets de-encapsulated, so it opens up, and it says, hey, I'm trying to get to LA. How do I get there? The router says, hey, I know how to get there. You need to go out this gateway. Cool, no problem. Re-encapsulates the information, and it hits another router, right? De-encapsulates. And as it hits this network, okay, it does it again. It says, it opens it up. It says, hey, how do I get to this network in LA? And the router says, yep, I know how you get there. You need to go out of this gateway. De-encapsulates it again, gets it ready for transportation, and shows up, and then voila, it shows up at its network right here. So that's kind of an example of how it re-encapsulates, de-encapsulates as it hits the different networks, right? So as that data hits the different areas, it knows where to go. Very, very similar to that UPS truck, very similar to that USPS truck when they are delivering, when you send something FedEx ground or whatever. More than likely, they are going to hit different types of hubs, right? They're going to hit different hubs. They're going to hit different routers, essentially, which means those are the different areas in which they are going to hand off the package so it can get to where it needs to get to. Data link layer protocols are defined by engineering organizations, the IEEE, ITU, the ISO, and American Standards, the ANSI. All right, let's talk about topologies. The topology of a network is arranged in a relationship of the network devices and the interconnections between them. There are two types of topologies used when describing networks. We have the physical topology, which shows the physical connections and how devices are interconnected. And the logical topology identifies the virtual connections between devices using device interfaces and IP address schemes. Now, Packet Tracer has a very good feel for this, which is pretty cool. So what I did was I went on ahead and drew a quick little topology here. And we talk about the physical view and the logical view. And if I click on the logical, obviously the logical tab was already clicked on here. This is what it looks like from a logical standpoint. Now, if I click on the physical, as you can see, I have a networking closet. If I were to blow this up a little bit more, you can see that. Here's my networking closet, my rack, and all of my Ethernet cables are going out of the door, or excuse me, out of the wall somewhere, plugged into my switch. And then I have a router and a server, things of that nature. Also have a computer in here as well. But if I go back to my logical view, it shows what it would look like from a logical sense. So this is a great way to get representations as far as how you would set something up, or how it would look from a logical sense. I would say network architects would use this very, very well if you were trying to build out a network. They would definitely go from physical and logical. But having that logical view first is very, very key. So it makes it easier to understand where everything is. So if there's a break somewhere, they can kind of trace it and kind of see what needs to happen from there. There are three common physical wide area network topologies. We have point-to-point, we have hub and spoke, and we have a mesh topology. Let's take a look at some of these. Physical point-to-point topologies directly connect two nodes together. The nodes may not share the media with other hosts, so it's just like from router to router, right? Because of the frames on the media can only travel to and from two nodes, point-to-point WAN protocols can be very, very simple. Makes things a lot simpler to have these. Now, Let's take a look at these local area network topologies, because some of these may look very familiar. Because I guarantee one of them you're doing right now in your own house. As a matter of fact, I want you to tell me, send me an email on which topology you think you're using in your house right now. End devices in local area networks are typically interconnected using a star or extended star topology. Star and extended star topologies are easy to install, very scalable, and easy to troubleshoot, right? So early Ethernet and legacy token ring topologies provide two additional topologies, bus and ring. Like, they don't use these anymore. These are old school. You know, they all kind of need to be talking to each other. If there's a break in the line somewhere, then they all would not talk to each other at all. But typically in your house, you probably should have a star topology. Essentially, you know, you're going to have your, let me pull out the pin here. You know, you'll have your cable coming in off the street. That's going to go into a modem, which you should know what that does. It converts analog signals into digital. And then that modem's going to go into your wonderful Soho router, right? By the way, a Soho router is a layer 1, 2, and a 3 all in one in your house. So you got the Ethernet cable going into your Soho router, and then you may have, say, your smart TV, you may have your PS5, and I'll just put an Xbox in there because some of you all love Xbox. You may have an iPhone in there somewhere. Here's your phone. May have another PC. And say like your TV is all hooked up Ethernet. PlayStation's hooked up Ethernet. Phone is communicating wirelessly. PC may be hardwired in. So this is a typical star topology. Typical star topology. And you may have a couple other devices somewhere else throughout the house. All right, let's move on here. So half duplex communication only allows one device to send or receive at the same time or on a shared medium, used in wide local area networks, legacy bus topologies, and Ethernet hubs. Full duplex communication allows both devices to simultaneously transmit and receive on a shared medium, and Ethernet switches operate in full duplex mode. So that means it's on both sides of that highway, right? Full duplex. They both can transmit at the same time without too many issues there. So to give you another example on what half duplex will kind of look like, I want you to take a look at this video here. So we have, essentially this is a road, right? We see this road here. And this road, let's just call this road a medium. This could be a Ethernet cable, fiber, physical medium, all that good stuff, something that connects our networks, okay? So half duplex, only one at a time, right? So I want you to think of this flag person here. And she's standing here with the stop sign. Either you can go or you can't go, right? So this is a good example of how items can go on a medium in half duplex, but only one at a time, right? Only one at a time. So notice how this car is going. This person is stopping again. So we're stopping the traffic here. Here's another example. Here's our physical medium right here. And this car is the data, the throughput, as you saw some of my older videos, right? And this car goes as well, one at a time. So this road would be operating in half duplex mode, right? One at a time. Full duplex would be that they all are moving, like there's no restrictions at all, right? No restrictions whatsoever. Contention-based access. All nodes operate in half duplex, competing for use of the medium, as we saw in that video, competing, right? Examples are carrier sense multiple access with collision detection, used on legacy bus topology Ethernet, and carrier sense multiple access with collision avoidance, used on wireless local area networks. So let me ask you a question. I want you to send me an email. I want to know what IEEE standard is associated with CSMA CD, and I want to know what IEEE standard is associated with CSMA CA. Send me an email on that, please. Okay. Controlled access, deterministic access, where each node has its own time on the medium, used on legacy networks such as the token ring, which is kind of really old. CSMA operates in half duplex mode, where only one device sends and receives at a time. Again, going back to that video, one device sends one at a time, right? That's that flag person that has the flag. You may go, stop, slow, all that good stuff. Uses a collision detection process to govern which device can send and what happens if the multiple devices send at the same time. So CSMA CD, collision detection process, device transmitted simultaneously will result in a signal collision on a shared medium. Devices detect the collision. Devices wait random periods of time to retransmit the data. So it's kind of like if you think about going to a stop sign, go to a four-way stop sign, and all four cars decide to get there at the same time. Instead of everybody hitting the gas at the same time, there will be a collision, right? Usually the person on the right needs to wait. It's kind of like we all kind of wait, we retransmit, break, stop, break, retransmit. Who's going to go first? That's kind of what that is. Okay, moving on here. CSMA CA operates in half duplex mode, where only one device sends at a time. We got that. When transmitting devices, CSMA CA, collision avoidance. When transmitting devices also includes the time duration needed for transmission. Other devices on the shared medium receive this time duration information and know how long the medium will be unavailable. So essentially knows how long it's been sitting there. The data link frame. Now, when we get into this, I want you to think of, because the data link frame talks, when the frames come in, it talks about, it has a header, the data, and the trailer. So what I want you to think of is, let me pull out my magical pen here. I'm going to draw a picture. I'm going to call this the Metrolink train. Okay. And this right here is where people hang out, or people ride the train here. And then we have the back of the train. So if you've seen those Metrolink trains, it seems like there's like engines on both sides. It looks like operators can be on both sides, which is crazy. So anyway, and if you know Metrolink is the local train here in Southern California. So the header, I want you to think of the header as the actual train. That is the engine of the train, beginning of the train. The data are the passengers inside of the train. And then the trailer essentially is the back of the train. It's the guy in the back that makes sure that everything is okay. You know, everything all looks good. Everything's looking great here, per se. That's the trailer. So I want you to think of that. When you see the header, the data, and the trailer, each one of these has a role. Obviously, the end result is to get the data to layer 7 of the OSI. That's the main result there. So as we talked about, we have our different fields here. We have the frame start and stop, identifies beginning error of the frame, end of the frame, Addressing indicates source and destination nodes. Type identifies encapsulated layer 3 protocols. Control identifies flow control services. And then the data contains the frame payload. That's what we're trying to get to, right? This is where essentially we're trying to get all of this up to OSI layers as much as we can. That's what we see. And then error detection used for determining transmission errors. Make sure that there's no issues. Make sure there's no troubles with the data. And this is a good representation again, and as we talked about earlier in the video, how the information gets encapsulated, de-encapsulates it, and it forwards it to the next network, encapsulates, de-encapsulates, forward to the next network. So these routers essentially, if you remember the example that I gave, this is LA, file destination LA, and this person's here, sitting here in Riverside, California, the 951, all that good stuff. And he wants to send information to this file destination or this person in LA, and it's going to go out through these little NICs here. It's going to hit these routers, and as it goes there, it's going to go through layer 2, layer 3 protocols, layer 2, layer 3. So this is the encapsulation, decapsulation, encapsulation until it actually gets to its final destination. That's how the layer 2 protocols, that's how they essentially work there. So I wanted to show you really quick a little activity here in Packet Tracer where it's going to show the layer 1 and layer 2 in action. So what I did was I configured some of these end devices here. I just gave it a basic 192.168.1.2 all on a subnet mask. The first 24 bits are on right now, so this would be a WAC 24. So I have this little file server set here on an IP of, let's go in here, 192.168.1.7. So what I'm going to do is I'm going to ping this server here, and I'm going to ping it from this computer here. So go to command prompt here. I'm going to type in 192. I'm sorry, add in ping first. 192.168.1.7. I'm going to press enter. All right, and I'm going to show you this in action. I have it in simulation here. What's going to happen is, as I advance forward again, the switch is actually going to send out a broadcast. Okay, it says, hey, who has this IP address? Tell this person this MAC address, all that good stuff. There's a protocol that's associated with that. And then after a while, it responds and says, hey, that's me. And here's the information that you asked for, which is your ping request. So let's take a look at that. Let's inspect that. Let's take a look at these different levels here. So my initial, here's the initial, PC1 here, goes out the Ethernet frame, and there's my destination. So I'm sending out a packet to my destination IP, 192.168.1.7. Now, the full FFF, if you see all that capsule, that is essentially, that's ARP. That's Address Resolution Protocol. That's the broadcast it sends out. It says, hey, who has this? Please tell this person that. All that good stuff. Then as it continues, let's go on to the next switch here. Okay. It gets to the switch. Okay. It ARPs again. And then it finds out who it belongs to, and then it goes to actually where it needs to get to. So let's inspect that data here. Let's see here. Uh-oh. Lost it here. There we go. So now it actually reached a layer 3 because now it has the IP address information. So started layer 1, layer 2. Once it gets to its destination where it needs to get to, then layer 3 obviously comes into play here, which is at 192.168.1.7. The logical topology and physical meter determine the data link protocol used. So we have Ethernet, okay, 802.11, wireless, point-to-point, high-level data link control, and frame relay. Each one of these protocols perform media access control for specific logical topologies. All right, ladies and gentlemen, that is going to conclude Module 6. Stay tuned for the next video. Have a good one.